Welcome back. Today we're going to continue with functions, and functions again is a topic that will be sort of carrying on throughout the rest of the course. And for what we're going to be looking at is going to be a type of function we have been looking at rather frequently, where we have had an equation form. But in the case of the details regarding this particular item, okay, we have with quadratic functions, okay, and okay, like we've had, quadratic equation to solve for, and we've had various types or various methods of solving, like the zero product property, the square root property of equality, the quadratic formula, and in the case of what we have regarding quadratic functions. And there will be a couple of layouts that we will have for quadratic functions, and we will be translating from one context to the other. And okay, so just getting things squared away. And we have regarding quadratic functions. Okay, and we have by definition, okay, so you have a quadratic function. Okay, a quadratic function. Okay, that is going to be a second degree function. Whose standard form is going to be, and again, we're going to be referencing the xy coordinate system. Okay, so we're going to have that y is equal to f of x, and we have is equal to ax squared plus bx plus c. And just like in the quadratic equation, okay, the leading coefficient a, that is going to be non-zero in value. And for what we have in the case of second degree, for a second degree function, we're looking at second degree in terms of the variable x. Okay, so you have x to the second. Okay, and again, this is the standard form, and we're going to be getting back to this form, but for the other type of layout, okay, this is going to be what is regarded as the vertex form of a quadratic function. And there'll be a change up in terms of the variables that will be utilized. Okay, but we're still going to have the letter A as well as the letter X in place. And for what we have for the vertex form of a quadratic function, okay, so here we're going to have that y is equal to f of x and we have, this time we're still going to have the same letter A, and this time instead of x squared plus bx plus c in the follow through, okay, we're going to have the quantity of x minus h. We have this difference binomial is to the second power, and we have followed by the addition of k. And just like what we have in the standard form, okay, again, the coefficient a is non-negligible. And for the vertex form, for what we're going to have regarding the behavior of the graph of a quadratic function, okay, first of all, okay, for the leading coefficient a, say if the sign value is positive, that is where a is greater than 0, then you're going to have the graph to open up from a point. And this is where the h and the k will come in. Okay, so if a is positive, then the graph is going to open up from the vertex. And the vertex would be in the xy coordinate system, but the numbers representing h and k will form the x and y coordinates that will define this vertex. Okay, so this is whenever the leading coefficient a is positive. But now just to change it up, okay, say that if the leading coefficient, okay, instead of being positive, okay, if this winds up being negative, okay, so I have a change in the sign value of a, and this is going to change the direction for how the graph is going to open from the vertex. In this case, it's going to open downward from the vertex. Okay, so if a is positive, then the graph opens up from the vertex. Again, if the leading coefficient a is negative, then the graph is going to open down from the vertex. Okay, and now we have involving the letter h. Now, you're going to have just like a lot of even functions. Okay, you're going to have the graph of quadratic function to be split up into equal halves that will mirror each other. And you're going to have like a visual dividing line, okay, that will split the halves of the graph of a quadratic function. And this is going to be what is referred to as the axis of symmetry. Kind of like the other week when we looked at even functions, you had like the y-axis happen to be the axis of symmetry. But for what we had in the case of quadratic functions, now you could have the axis of symmetry to be the y-axis, but if it's not, you will have the general representation where we have that x is equal to h. Okay, and this is going to be a visual vertical line. Okay, that's going to divide the graph of y is equal to f of x into equal mirroring halves. Like you'll have a left half and a right half. Okay, so you have x is equal to h, and we're looking at this same h from the vertex form layout expression for the vertex form of a quadratic function. Okay, now where we have h also involved, okay, again, this is just going back to vertex. for the vertex HK. Okay, that is going to be the point from which the function is going to open. And in terms of the kind of graph a quadratic function will be, it's going to be what is referred to as a parabola. And just a couple of visual layouts. Again, so we have working with the XY coordinate system. Okay, and we'll have, in the case of the graph of a quadratic function, okay, so we'll have a point here, and just let this be the vertex, HK. And for this figure, okay, it is supposed to, both of the halves are supposed to be mirroring each other. Now for the red line that you see here, okay, again, that's going to be the axis of symmetry. Again, we have x is equal to h, and the axis of symmetry always passes through the vertex. Okay, and again, the graph of the parabola, you'll have equal halves mirroring each other. And for what we have with this particular function, okay, so you have y is equal to f of x. And I'll just go ahead and just lay out both the standard and the vertex form. So you have ax squared plus bx plus c, and again, have equal to the square of x minus h plus k. All right, and if you notice, k, the opening from the vertex, you had the graph to be opening upward. Okay, so in this particular case, right, this is where a is positive. And again, you have that f of x is opening up from the vertex. Again, we're still looking at the same a. And for what we have in this particular regard, okay, now when you have to be opening up from the vertex, when it opens up from the vertex, okay, notice you have, going back to relative minima and maxima, when the graph opens up, okay, now the vertex is going to be the minimum. Or the location of the minimum. So these are sort of the foundational mechanics of what we have for the graph of a quadratic function as well as its features. Again, whenever the coefficient is positive, you have the graph to be opening up from the vertex, where the vertex in this case is going to be the minimum. Okay, and just taking what I have here and just providing modification. Okay, a lot of similar history. It's going to be repeating, and this time we have with the parabola, we had to be opening downward. Okay, so you have a is less than 0. And this time you're going to have the graph, okay, to be opening down from the vertex. And in this particular case, right, so you still have the vertex HK, still have the axis of symmetry, x is equal to h, and again it divides the parabola into equal sections, and it always passes through the vertex. And whenever the graph opens down from the vertex, this time around, okay, you have the vertex to be the relative peak point, and this will be regarded as the maximum. Okay, all right. So these are just general illustrations of what we have here. Now, for what we have in the case of a quadratic function, okay, that has specific numerical coefficients, and let's say that as an example, okay, say if we have say we have f of x is equal to, let's say we have x minus 2 raised to the second, followed by the addition of 5. Again, just for the introductory elements, okay, say if we were to first of all determine the direction that the graph opens, and transitioning from A to H. Okay, so you have the axis of symmetry. And once you have the axis of symmetry, you already have half of the ordered pair of the vertex. Okay, so for what we have with this form, okay, we already have a specified version of a function that is laid out in vertex form. So again, we have y, we have f of x, and we have, again, so you have a times the square of the quantity of x minus h followed by the addition of k. All right. Now, for this particular function, again, we have f of x is equal to, okay, we are looking at the square of x minus 2 followed by the addition of 5. Okay, and if you notice, we don't have any explicit value in front of the square of x minus 2. And so we have implicit, okay, that, okay, you don't have a negative sign, just have this implicit version, okay, of what is otherwise going to be 1 times the square of the quantity of x minus 2 followed by the addition of 5. Okay, so just for what we have for the lead-in, okay, so for a is going to be equal to 1. And in this particular case, right, so a is going to be positive. Okay, and again, if the leading coefficient is positive, then the direction upon which the graph is going to open is going to be up. Okay, now for that which represents the square of x minus h, okay, that's going to be the lead-in for the determination of the axis of symmetry and also half of, or namely the first coordinate of what is going to be in the vertex. Okay, so we have for x minus h, okay, this will be represented by x minus 2. Now, while we are not using the zero product property, strictly speaking, just think of it like this: if x minus h, if you had equal to 0, you would have the x is equal to h. And your h value is going to be the 0 of the binomial x minus 2. So if I were to envision, okay, so we have x minus 2 is equal to 0. And if x minus 2 is equal to 0, okay, we have the x is equal to 2. Okay, and so for the axis of symmetry, and use AOS for shorthand, axis of symmetry. So you're going to have the x is equal to h, and that h value will be 2. And for what we have in terms of the k value, okay, so the value of k is going to be the constant, okay, that is lagging at the end. Okay, so we have plus k, and in this case we have plus 5. Say that k is equal to 5. And so for what we have in the case of the vertex, okay, so you have h and k. So h will be the x value from setting to 0, that which represents x minus h. So again, we have h is at 2. And once again, we have k to be at 5. All right, so those are our introductory components for what we have for this function expressed in vertex form. And to give a bit of a visual, I think I still have this up. Okay, so for what we have in the case of our function, okay, so y is equal to f of x is equal to the square of x minus 2 followed by the addition of 5. And again, okay, if you notice, okay, we have with 2, 5, okay, that is going to be the vertex. And from the vertex, again, we're going to have that the graph is opening up. And if you notice, for the dashed red line, okay, that is running through the middle. Okay, so you have, again, this is going to be the axis of symmetry. Whereupon we have that x is equal to 2. All right. Now, in the case of another quadratic function, okay, that we have in vertex form, and if we're looking at the direction the graph opens, as well as this axis of symmetry and corresponding vertex. And let's say that if we have so we have that f of x, and let's say we have negative 2 times the square of the quantity of x plus 5 minus 10. Again, we have another vertex form. And just looking at what we have in the correspondence. Okay, so just lining things up. Okay, so you have this quadratic function. Okay, we have provided in vertex form. Okay, so we have looking at what we have now. Okay, so you have for a, okay, in this layout, you have a is equal to negative 2. So we have that a is less than 0. Okay, and for any negative coefficients, okay, this is going to signal that this particular function is going to open down from the vertex. And if you notice, okay, for what we have in the case of the determination of the axis of symmetry, we need to find, okay, what h is going to be. And if you notice, we have x minus h is represented by, instead of a binomial of subtraction, we have one of addition. Okay, and still, we're looking at solving for x once we set that which represents x minus h equal to 0. So in this case, we have x plus 5 is equal to 0. And in this case, we're going to have that x is equal to negative 5. Okay, and that is going to be the h value that corresponds. So we have for the axis of symmetry, okay, so x is equal to h. Okay, so that is going to be at negative 5. And we have also, okay, we have the algorithm has plus k. And for what we have in the specific function, okay, we have the operation of subtraction. So like subtraction is the addition of a negative. And for what I have here, the k value lands at negative 10. Okay, and so we have with x equal to h in store, as well as the k value already specified. Okay, so it's going to turn out that the location of the vertex, or the location where the graph opens downward, is going to be at negative 5, negative 10. All right, and so just looking at what we have now, and just for the for the dynamics. Okay, they'll be played out. Okay, so we have for y, or f of x, is equal to -2 times the square of x plus 5, followed by the subtraction of 10. Okay, so again, okay, from the vertex. Okay, so you have the graph is going to be opening downward. And again, the red line, okay, that's going to be the axis of symmetry, where we have x is equal to -5. And again, the axis of symmetry always passes through the vertex, which we have at -5, -10. All right, and we'll be looking at further characteristics, okay, that will define, okay, what we have for a quadratic function. And tell you what, just in the case of what we have concerning quadratic functions, and let's say that if we have, let's say just a couple of items here. Okay, so again, determine the direction f of x opens, the axis of symmetry, and the vertex. And we'll say we have for the following functions, and we'll say that we have, first of all, we'll say that we have f of x is going to be equal to 3 times the square of x minus 7. And also with our other function, we'll say that we have f of x is equal to -2 times the square of x plus 6 plus 25. Okay, so no graphing necessary. Just determine the direction that f of x opens, the axis of symmetry, as well as the vertex. And we'll discuss in just a few moments. Okay, So for these two functions, okay, we're looking at the direction that the graph opens, as well as the determination of the axis of symmetry, as well as the vertex. Okay, so we have, first of all, okay, we have, with the first function, okay, we have that y is equal to f of x is equal to 3 times, okay, the square of the binomial x minus 7. Okay, so just first things first. Okay, so we have for a, okay, we have a is equal to 3, which is positive. And any quadratic function that has a positive leading coefficient, okay, is going to have the graph to open up from the vertex. Okay. And in pursuit of what we have for the axis of symmetry, okay, so you have x minus h is represented by x minus 7. And the h value is going to be the 0 of x minus 7. Okay, so you have the x is equal to 7. Thus, the axis of symmetry will be at x is equal to 7. Now for the k value, okay, notice that there is no constant, positive or negative, that follows 3 times the square of x minus 7. So you have a void here, and this will signal that k is equal to 0. So you have for the vertex, okay, the location will be at 7, 0. And just looking at the graph on this one. And again, so you have with the axis of symmetry, again, you have x equal to 7, and it's going to pass through the vertex. And again, the vertex we have at 7, 0. And again, from this point, okay, the graph is going to be opening upward. And among the other points through which the parabola is going to pass, you have 6, 3, 8, 3, 5, 12, 9, 12. So we have, if you notice, okay, we have for these points, okay, at the same elevation, you have 6, 3, and 8, 3. And notice you're going to have 6, 3 is equal in distance from the axis of symmetry as 8, 3. Likewise, you're moving just as far to the left once you get to y is equal to 12, jutting out to the left to get to 5, 12, and equal in distance, but out to the right we have at 9, 12. So you have symmetry throughout. Now, for what we have in the case of our other function, okay, so we have also in vertex form, so we were able to go ahead and determine the value of a. So we have a is equal to negative 2. So you have that a is less than 0. So in this case, you're going to have that the graph opens downward from the vertex. Again, in creating the pathway to the determination of the axis of symmetry as well as the vertex. Okay, so you have x minus h. Okay, we have represented by x plus 6. So for setting x plus 6 equal to 0, we have that the h value is going to be at x is equal to negative 6. So you have with the axis of symmetry. Okay, so you have x equals h is equal to, or x is equal to -6. And for the k value, okay, that's going to be at +25. And we'll have for the vertex, okay, so you have h at -6, k at 25. So with this ordered pair, okay, we're going to end up at -6, 25. All right. And just looking at this function in terms of the visual layout. Okay, so you have with the vertex, okay, you have at -625, and the parabola opens downward. And again, you have the axis of symmetry, x equal to -6, okay, vertical line that passes right through the vertex. And again, we have other points through which the graph is going to pass. You have like -723, -523, -817, -417, and you're going to have an infinite number of points through which the parabola is going to pass. Okay, so we have our foundational characteristics, okay, for the graph of a quadratic function expressed in vertex form. Now, let's say that if we expand the model and sort of tie in some of our previous items regarding functions. And let's say if we have a quadratic function, okay, and I'm just going to put this in vertex form as well. And let's say that if we have given f of x is equal to the square of x plus 4, followed by the subtraction of 4, and you're looking at trying to determine and say we have, first of all, okay, we say we have the direction f of x opens. Again, the axis of symmetry. The vertex once again, okay. And also other items, okay, we see we have determining the x-intercepts, if there are any. As well as y-intercepts. And also at least 5 points. Okay, so you have this particular quadratic function, and just creating the familiar pathways, okay, to finding out the direction that the graph opens, as well as the axis of symmetry and the vertex. Again, just using the general layout for that which defines the vertex form of a quadratic function. Okay. Alright. Okay, so we have for this particular quadratic function. Okay, so again we have a, which is implicitly going to be once again at 1, kind of like our earlier example. Okay, so you have a is equal to 1. So a is positive. So we have that the graph of f of x opens up. Okay. And for h and k, now the h value will be the 0 of our x expression. So we have that expression is going to be the binomial x plus 4. And if x plus 4 is equal to 0, okay, so we have the x is equal to negative 4. And from this case, you're going to have the axis of symmetry. You have x is equal to h, and this in turn is going to be negative 4. And as for the k value, okay, we have the subtraction of 4. Okay, so you have k is equal to negative 4. And so the location of the vertex will be where both the x and the y coordinates, or the h and k values, will be the same. So we have negative 4, negative 4. All right, so you have these three components. Okay, now for the intercepts. Okay, so for the x-intercepts and the y-intercepts. Okay, now for the x-intercepts, okay, now in coordinate fashion, okay, we're looking at solving for x while setting y to 0. Okay, so for what we have in this case, right? So we got, okay, so you have y is equal to f of x. And again, we have is equal to the square of x plus 4 minus 4. Okay. And setting things up, so we're going to set y equal to 0. You have y and f of x, one and the same. Okay, so setting equal to 0. So you're going to have in the rewrite, we're going to have that 0 is equal to the square of x plus 4 followed by the subtraction of 4. Okay. And so what you can do is that you could square out x plus 4 and use the 0 product property to solve for x, but another pathway or avenue is to just isolate the square of x plus 4. So I can just move this constant 4 over by adding. So you got 0 plus 4 is 4. And we had that 4 is equal to the square of x plus 4. Again, you could create a pathway that leads to the zero product property, or if I isolate the square of x plus 4, I can utilize the square root property of equality. And what I'm going to do here is just switch the sides here, okay, like b is equal to a, and just put this in the context of a is equal to b. All right, so I have the square of x plus 4 is equal to 4. Again, just with the square root property of equality. Again, if you have x squared equal to a constant, you have that x equal to plus or minus the square root of that constant. Okay, so just on the same note here. So going from the square of x plus 4 to x plus 4. Okay, so you have plus or minus the square root of 4. Okay, so transitioning from the square of x plus 4 to x plus 4. Okay, this is equal to plus or minus the square root of 4, so this would be plus or minus 2. All right, and looking at solving for x. Okay, so there will be two distinct values that we will arrive at for x. So you have at the one end, we have x plus 4 is equal to negative 2. We have at the other end, we have x plus 4 is equal to positive 2. Okay. All right, so if we had the x plus 4 is equal to negative 2, okay, we have taking 4 away from both sides. We're going to have the x is equal to negative 6. And for what we have for x plus 4 is equal to 2, if I take 4 away from both sides, we have the x is equal to negative 2. Right. So we have two distinct x values. So this means that there will be two x-intercepts. Okay, so you have x-intercepts, okay, like in equation terms, you have x equal to negative 6, x equal to negative 2. And for what we have in terms of ordered pairs, okay, x equals negative 6 refers to negative 6 is 0, and x equals negative 2 refers to negative 2, 0. Now for what we have in terms of any y-intercept, so you have a role reversal in terms of what to solve for and what to set equal to 0. So this time we're looking at, for the y-intercepts, okay, the general coordinates you have with 0y. And just looking at what we have here, okay, so we're looking at solving for y as x is set to 0. Okay, so for f of x, we say that's going to be f of 0. And the square of x plus 4, we have the square of 0 plus 4 minus 4. And we have 0 plus 4 is 4. Which would be squared. And we have, take away 4. 4 squared is 16. And we have 16 minus 4 is equal to 12. Okay, and there's only one value for y. And we have just for this, there's going to be just one y-intercept. Okay, so you have y is equal to 12, or in coordinate terms on the y-axis. Okay, we're going to have the ordered pair with 0, 12. Okay, so just compositing together what we have. Okay, so just for the kind of the lead into the points on the graph of this function. again, for the direction that the graph of the function opens. Okay, so again, so this is going to open up. Again, we had the axis of symmetry. Okay, that earlier was that x is equal to -4. And for the vertex, okay, again, you had the same h and k values, or x and y values. So you have -4, -4. Now for the x-intercepts, you can say x equals -6, x equals -2. But putting in terms of points, okay, so you have -6, 0. And -2, 0. And for the y-intercept, okay, there's only one. Okay, so you have at 0, 12. Okay, so with the vertex and intercepts, now we've got 4 points. And if I'm looking at for at least 5 points, now a parabola is going to have an infinite number of points, and you could use substitution and find out like another point in this fashion. But let's say that if you're using the intercepts and the axis of symmetry, okay, to find out okay what a possible fifth point is going to be. Okay, all right. So you had the axis of symmetry, the red line. You have x equal to -4. And you got the vertex located at -4, -4. X-intercepts, you have -2, 0, -6, 0. And we have the y-intercept, we have at 0, 12. Okay. And if you notice, okay, we have for the x-intercepts, you have -2, 0 and -6, 0. And if you notice, we have equidistant, okay, from the axis of symmetry, again, which we have at x is equal to -4. And just looking at what we have here, if you notice, you have -2, 0. This is going to be 2 places to the right of the axis of symmetry. And -6, 0 is going to be 2 places to the left. And let's say that if I go up, okay, to y is equal to 12. Okay, so going from the axis of symmetry, so you have like -4, 12. And if I go out to the right to 0, 12, so I will have ended up going 4 places to the right. And a possible fifth point that you can label will be level with the y-intercept. So if I were to go 4 places to the left, okay, so your y value is at 12, and 4 places to the left of -4, this is going to land at -8. So a possible fifth point that you can label will be that which is in line with mirroring what we have across the axis of symmetry away from the y-intercept. So in this case, you would have at -8, 12. All right. And again, so these are just cases of what we have for characteristics of quadratic functions, especially when they are presented in the vertex form. Now, from the start, now we've had a standard form as well as a vertex form. And let's say that we're looking at converting between the types of expressions. Okay, so for this part, I'll just call this looking at converting between standard and vertex forms. Again, for the standard form of a quadratic function, again, like this setup for the use of the quadratic formula. Again, we have ax squared plus bx plus c whereupon a does not equal to 0, and for the vertex form, you can have a times the square of x minus h, followed by the addition of k, and again, a does not equal to 0. Now, in terms of conversions, now we'll look at converting what we have going from standard to vertex form. And once you convert to vertex form, determine what the vertex will be. And we'll say we have first case. We'll say we have f of x is equal to x squared plus 6x plus 8. Okay, now looking at converting from the standard form to its vertex form. Okay, so just laying the groundwork. Okay, so again we have f of x is equal to x squared plus 6x plus 8. Again, that is the standard form. Okay, now in looking at arriving to the vertex form, okay, notice the vertex form has the square of a binomial. Okay, and the existence of the square of a binomial can come from what is referred to as a squared trinomial. Okay, now if you notice we have x squared plus 6x plus 8. Now this is factorable, but it is not a squared trinomial. Again, like x squared plus 6x plus 8. Okay, this is factorable to x plus 2 and x plus 4. But I'm looking at, in the mix, a trinomial that will have the same binomial times itself going into it and creating this type of existence. Okay, what I'm going to do here initially, okay, is that I'm going to separate using parentheses the x squared and 6x terms apart from the 8 that follows. Okay, so I have x squared plus 6x followed by the addition of 8. Now in terms of what I can do and following through, so I'm going to create a square trinomial, and this will be through a process of what is referred to as completing the square. So looking at what we have at this stage, okay, for completing the square. So how do I go about completing the square? Well, first of all, okay, you got in parentheses, you have x squared plus 6x, and I want the first term inside the parentheses to be x squared, y squared, whatever independent variable we're dealing with. I want that variable to the second power with no coefficient other than 1 in front of it, should there be a numerical coefficient. But I want the first term in the parentheses to be the square of the independent variable. And now for setting up what we have for the completion of the square, okay, I want to take the coefficient that is next to the first order variable. In this case, so the first order variable term is 6x, and I'm going to take the coefficient of this, and regardless of how the coefficient appears, whether it is a positive or negative, or if it's a fraction, rational number, irrational number, for the completion of the square, I'm going to take half of the coefficient and square. So you got 6's alongside x. So half of 6 is going to be 3. And the square of 3 is going to be at 9. Okay, so got in the initial steps, okay, for completing the square, okay, next thing that arises, okay, so I got half of 6 is 3, 3 squared is 9, okay, and the question is, okay, what am I going to do with 9? Well, I'm going to take that constant and add to the variable terms. So we have x squared plus 6x plus 9 . Okay, and I'm going to, in the follow through, if you notice, okay, I want to keep things in balance with x squared plus 6x plus 8. But right now, by adding 9, I have x squared plus 6x, and 9 and 8 will make 17. But I want to keep things in balance. Okay, so I just added 9. Okay, so to get it back to level 1, so to speak, I'm going to, whatever I add at the front, I want to offset at the end by balancing. You have like plus 9 at the front, minus 9 at the back, and I'm back to x squared plus 6x plus 8. But now, getting closer to the vertex form. Alright, so right now, I have x squared plus 6x plus 9, and I have 8 minus 9 becomes negative 1. Okay, now x squared plus 6x plus 8 is not a square trinomial. However, x squared plus 6x plus 9 is. And guess what? So writing this as the square of a binomial expression. Okay, so you notice with x squared plus 6x plus 9. Okay, now x squared is going to be the square of x. All right, and in terms of how this 9 came into existence, well, this arrived upon squaring out a positive 3. And guess what? Whatever number I square out, this is going to appear in the vertex form. So I squared out a positive 3. So in this particular case, all right, so the vertex form Okay, so this is going to be the square of x plus 3 followed by the subtraction of 1. And just determining, okay, what the vertex is going to be. Okay. So again, we got the vertex form, and we have implicitly. Okay, so you have that a is equal to 1. And since I'm looking at just the vertex, I'm going to be interested in just the h and the k values. Okay, so for x minus h, you have represented by x plus 3. So if I set x plus 3 to 0, okay, so you have that x is equal to negative 3. Okay, so you're going to have that x is equal to h is equal to negative 3. And for what we have, again, for the k value, okay, you have plus k represented by the subtraction of 1. So you have that k is equal to negative 1. And so for the vertex, okay, that is going to be located at negative 3, negative 1. All right. Now, let me give you another case here. And let's say that I'll still have the first term at x squared. And we'll say that we have f of x is equal to x squared minus 8x. And we'll say that we have plus 20. Okay, so you have x squared minus 8x plus 20. Okay, now looking at the vertex form on this one. Okay. Okay, so you have f of x is equal to x squared minus 8x plus 20. Okay, so once again, you're going to have the standard form. And I want to write this in terms of the vertex form. So I'm going to form a squared trinomial, okay, and this will originate from the variable terms which I have with x squared minus 8x. And just as I had separated x squared plus 6x apart from 8, I'm going to do likewise with x squared minus 8x with respect to 20. Okay, and in terms of crossing over, okay, to where we have in the stage of completing the square. I'll just use a little bit of shorthand here. CTS for complete the square. Okay, so for x squared minus 8x plus 20. Okay, so again, the first term inside the parentheses is x squared. Now for the first order x term, now the coefficient will be negative 8. And just like what I did with positive 6 from 6x earlier, I'm going to take half the number and square. And half of that number is going to reappear in the vertex form. So half of negative 8, okay, that is going to be negative 4. And the square of negative 4 times itself, this comes out to positive 16. So right now we have the quantity of x squared minus 8x followed by the addition of 16. Then we have plus 20. And if you notice again, we had to, I'm adding 16 at the front. And right now, if I don't offset the imbalance, okay, and we'll have like x squared minus 8x plus 36. But to get it back to plus 20, okay, whatever I add at the front, I'm going to take away at the back. So I'm going to deduct 16. So for now, we have x squared minus 8x plus 16. And this is going to be a squared trinomial. And 20 minus 16, okay, that is going to be a plus 4. And for what we have in arriving at the vertex form, okay, so x squared minus 8x plus 16. Okay, so x squared is going to be the square of x. And for the rest of the binomial, okay, we go back to the constant 16, which we added. And this originated from having squared out negative 4. Okay, so for what we have now, so the vertex form we have with the square of x minus 4 followed by the addition of 4. And just looking at what we're going to have for the vertex. Okay, so the h value had to be the 0 of x minus 4. So x is equal to h is equal to 4. Again, we have with the k value, that is going to be at 4. So h is 4, k is 4. And so we have for the vertex, okay, that will be 4, 4. And I tell you what, just for what we have, for the next few minutes, determine the vertex form and the vertex. Of let's say we have f of x is equal to, let's say we have x squared plus 10x plus 31. Okay, so for the next few moments, let's see what we get for the vertex form of this standard function layout and see what we get for the vertex as well. Okay, for this particular quadratic function, okay, which we have in standard form, okay, so you have x squared plus 10x plus 31, okay, and now for what we have here, okay, so converting to vertex form, and just like what I did with x squared plus 6x and x squared minus 8x, I'm going to set apart x squared plus 10x away from the constant. Okay, so I'm going to have for quantifying the variable terms, so I have x squared plus 10x put in the parentheses, and again we have followed by the addition of 31. And then we have in the follow through. Okay, so crossing over into the stage of completing the square. Okay, so you have x squared plus 10x followed by the addition of 31. Okay, and now again, so we have first term in the parentheses, we have x squared. Now for what I have for the first order x term, okay, the coefficient, okay, is a positive 10. And once again, we'll be taking half of the number and squaring. Okay, so we have half of 10 will make 5. And we have that 5 squared is equal to 25. Okay, and so for what we have in the follow through, okay, so we have f of x is equal to x squared plus 10x. Okay, and upon adding 25, I'm going to have a bit of a surplus with 25. Okay, so this would be, like at the moment, x squared plus 10x plus 56. But to get it back to being in level with 31, so I'm going to take away 25 at the end. So we're going to have f of x. Okay, so you have x squared plus 10x plus 25. And for the constants at the end, okay, so you have 31 minus 25, so that will leave us with plus 6. And for what we have in the case of the vertex form, so the remaining item is to rewrite this trinomial in terms of the square of the binomial. Okay, so right now, okay, so we got x squared is going to be the square of x. And again, I had formed this trinomial upon adding 25, which originated from squaring out a positive 5. And so we have in the translation, so x squared plus 10x plus 31 in the standard translates to what we have in the vertex form with the square of x plus 5 followed by the addition of 6. Again, just for the vertex. Okay, so we just go ahead and get the h and the k values. So for the h value, this will be the 0 of x plus 5. So we have x is equal to h is equal to negative 5. And again, we have with the k value, okay, the plus 6 refers to the k. And for the coordinates of the vertex, we're going to have at negative 5, 6. Okay, now, so far we've had the first term in the standard form to be x squared. I'm going to give you just a case of where we might have a raised coefficient. And let's say that if we have first of all, okay, so we have, we'll say we have f of x is equal to, and we'll say we have 2x squared plus, let's say we have 2x squared plus 20x. And we'll say we have plus 99. And I want to convert, okay, what I have to the vertex form. Okay, so looking at what we have in the process. Okay, so if I look at, once again, separating the variable terms apart from the constant. Okay, so I got the quantity 2x squared plus 20x plus 99. Okay, now there might be the temptation to try to go ahead and complete the square, but do not do this yet until what you have as your first term in the parentheses is x squared and only x squared. Okay, so I'm going to do here. Then I'll just copy this. Okay, so what I have here, okay, so I don't have x squared at the front, but 2x squared. So I'm going to factor out the 2 from the front. And just doing a little bit of color coding. Okay, so factoring out 2. So we have 2 times the quantity of x squared plus 10x followed by the addition of 99. Okay, now for what we have in the crossover to the completion of the square. Okay, so after factoring out 2 from 2x squared plus 20x. Okay, so like your a coefficient is going to be at 2. Now for the completion of the square. Okay, now the variable terms inside the parentheses upon factoring, we have x squared plus 10x. And once we have it resolved where the leading term in the parentheses is x squared, again, I take the coefficient of the first order x term. In this case, so we're going to have it 10. Again, divide by 2 and square out. So we're going to have half of 10 is 5. And 5 squared is equal to 25. Okay. So we have in the next phase. Okay, so you have f of x. So you have 2 times the quantity. Okay, we have of x squared plus 10x. And we have followed by the addition of 25. Okay, we have followed by 99. Okay, now in terms of whole new situation that's apart from the earlier examples. Okay, in the follow through after completing the square. Okay, we had the factoring of erase coefficients. Okay, now for the subsequent steps, now before what I have like in the earlier cases, like what I added at the front, inside the parentheses I took away at the back, like with plus 25, take away 25. But now with the multiple 2 factored out, okay, as I'm adding 25 inside the parentheses, I'm not adding just 25, but 2 times 25. And guess what? If I had just x squared plus 10x plus 25, no leading coefficient at the front, I'd have just been automatically taking 25 away. But with this 2 out the front, as I'm adding 25 within, at the front, I am adding overall 2 times 25. So you have like 2 times plus 25, so I'm actually adding 50. And guess what? To offset the imbalance, I'm not taking away just 25, but taking away 2 times 25. So for right now, say I have 2 times the quantity. So I have x squared plus 10x plus 25 and 99 minus 50. Okay, that is going to be 49. Okay, and if you have any trepidations, okay, about this stage, you can see, is this going to balance out to what I had before? Okay, so if I look at distributing, okay, so you got 2 over x squared is 2x squared. 2 over 10x is going to make 20x. Now 2 times 25 is 50. 50 plus 49 is 99. So we're on the right track. Now, for what we have now, you got 2 times the square, x squared plus 10x plus 25. So we have a squared trinomial. Okay, and in terms of what's going to represent x minus h, so going back to x squared plus 10x plus 25. Now, x squared is going to be the square of x. And again, we had the trinomial formed upon adding 25. And this 25 came about upon squaring out positive 5. And guess what? Any number I square out in the completion of the square step, that is going to reappear in the binomial in the vertex form. So in this case, we have 2 times the square of x plus 5, followed by the addition of 49. And as for the vertex, okay, so just looking at the h and the k values. Okay, so your a value is at 2, but for the h and the k amounts, okay, so you have, again, have x plus 5 is equal to 0, x is equal to -5, so you have that x is equal to h is equal to -5. And for what we have in terms of the k value, okay, so we have that k is equal to 49. And so we have with the coordinates, okay, so for the vertex hk, okay, this will end up at -5, 49. Okay, now there is another part, okay, that's going to lead into what is referred to as the end behavior of the graph of a function. Okay, and there'll be these things like whether the graph crosses or touches the x-axis, and for that part, okay, I'm going to say, but just to kind of give a little bit of a segue to some of the future topics, but also just kind of refurbishing exercises we have done previously, like the FOIL method and the zero product property. I would just call this part forming polynomials. From given zeros. I'll just give you a couple of cases here. And let's say that if we have okay, and we'll say that we have, if you have like writing f of x in a form that is factored and expanded given, and we'll say we have, let's say for the zeros, and we'll say that we have, let's say we have 0, 2, and we'll say we have 5. Okay, and think of this like your zeros. Okay, think of it like working backwards. Okay, so you have like x is equal to 0, x is equal to 2, and we have x is equal to 5. Okay. Okay, so again, we have x equal to 0, and we say that just originates from the variable x. And we say that x is equal to 2. Think of this like arriving from having set equal to 0 the binomial x minus 2. And for x equal to 5, we say that can come from setting equal to 0 the binomial x minus 5. So you have x equal to 0. If x minus 2 is 0, we have x is equal to 2. For x minus 5 equal to 0, we have x is equal to 5. You say that we have for a factored form of the polynomial, okay, for the variable expressions, okay, we have, again, taking in reverse and setting equal to 0. So we have, so you got x, and for 2, we say we have x minus 2, and from x equals 5, we say we have x minus 5. So this is one factored form. Okay, so if I were to use the zero product property, we have x at 0, x minus 2 equal to 0, x equals 2, x minus 5 equal to 0, x is equal to 5. Now looking at expanding, so if I were to multiply these expressions together, so you have x over the quantity of x minus 2, and so you have x squared minus 2x and then I can just multiply x minus 5. Okay, so if I were to FOIL out, okay, so I have x squared minus 2x from x times the quantity of x minus 2. And if I FOIL out, okay, like we have x squared times x, that is going to be x cubed. Outside product, we have x squared times negative 5. So we're going to have minus 5x squared. Inside product, we have negative 2x times x, so this will be a negative 2x squared. And negative 2x times negative 5, okay, so that would be a plus 10x. Okay, and once we assemble the like terms in the middle, we have for an expanded form, so we have that f of x is equal to x cubed minus 7x squared plus 10x. Okay, and just as last case here, if I'm looking for a factored and expanded form, and we'll say that we have for the zeros, we'll say that we have, let's say we have negative 1, negative 3, and we'll say we have 2 and 5. Okay. It's like we have x equal to negative 1. We say this comes from setting x plus 1 equal to 0. For x equal to negative 3, we say this will come from setting x plus 3 equal to 0. And for x equal to 2, we say this comes from setting x minus 2 to 0 And for the zero value of x equals 5, we say this comes from setting equal to 0 the binomial x minus 5. It could be those terms or any direct multiple. Okay, so we say we have as a factored form. So we say that we have f of x is equal to x plus 1 times the quantity of x plus 3. And we have times the quantity of x minus 2 and we have times the quantity of x minus 5. Okay. Now in terms of expanded form, what I'm going to do here, I'm going to cluster the first two and the last two binomial expressions. Okay, so if I FOIL out what I have between x plus 1 and x plus 3, we have x squared plus 3x plus x will make 4x. And 1 times 3, okay, so this will come out to 3. And for what I have with multiplying x minus 2 by x minus 5, FOILing out, x times x becomes x squared. Outside product we have negative 5x. Inside product we have negative 2x. And negative 5x minus 2x becomes negative 7x. And negative 2 times negative 5, okay, so this will be a positive 10. Okay. And, okay, so for the expanded form, now what you can do, as opposed to just FOILing out, okay, the regular way, it could do it like from the aforementioned version or approach from the first day of class. Okay, we have like the geometric FOIL approach. And what you can do here is that we can have a row column formation. So you have x squared plus 4x plus 3. And you have x squared minus 7x plus 10 I'm just going to do here, I'm just going to partition Okay, so looking at the products of the corresponding parts, so we'll just go column by column. So we have for the upper left hand section, okay, we have x squared times x squared, so this will be x to the 4th. Then we have negative 7x times x squared, so we have a negative 7x cubed. And then we have plus 10x squared to complete the first column. And then we have for the middle column, so you got x squared times 4x. So this will be 4x cubed. Then we have negative 7x times 4x. So this will be negative 28x squared. And then we have 10 times 4x. So this will make 40x. And for the last column, we have 3x squared. And then we have negative 7x times 3, so this will be negative 21x. And we have 10 times 3, so that is going to make 30. All right, so we have in terms of the expanded form, okay, so we have for f of x, okay, so looking at combining like terms together, so you have x to the fourth, okay, that is the only term of fourth order. And if I look at combining, let's see, our third degree terms, so you got minus 7x cubed plus 4x cubed, negative 7x cubed plus 4x cubed. This will leave us with negative 3x cubed. And for what we have in terms of the second order, so you got 10x squared minus 28x squared plus 3x squared. So you have 10 minus 28, that's negative 18. Negative 18x squared plus 3x squared, so this will leave us with negative 15x squared. And for the first degree x terms, we got 40x minus 21x, so this will leave us with 19x. And then finally, okay, we have with the constant, okay, so you have 30. And so this is one version of the expanded form, okay, that will have all those zeros involved, okay, and there'll be other items in the mix. Okay, if you notice, okay, so far we have a fourth order polynomial originating from 4 distinct zeros. And for this polynomial, okay, we have a third order polynomial originating from 3 distinct zeros. And in a lot of cases, okay, the degree of the polynomial and the number of zeros will be the same, but there can be some exceptions where you can have what will be like what's referred to as a raised multiplicity of a zero, and that's going to sort of tie in with the end behavior of the graph of a function and whether the graph is going to cross or touch the x-axis at particular locations. Okay, I'm just going to save that for later.